Yeah, welcome to viewers. Myself, D. Srinivas Rao. Now I am teaching strength of materials. So strength of materials we can call it as a mechanics of materials and mechanics of solids. So we can call as this as a mechanics of materials, mechanics of materials and mechanics of solids. So simply we can call as this as a SOM or SM, strength of materials, mechanics of materials and mechanics of solids. Okay. Now, so mechanics can be classified into two different categories. The first one is a rigid body mechanics. Rigid body mechanics, and the second one is a deformable body mechanics. So what is meant by deformable body and what is meant by rigid body? Let us take, I'm taking a material having any shape. In the two cases, having the same material, this is the first case, this is the second case. So I'm taking a 2 points, A as well as B, and here also taking a point A and B. So initially the distance between both the points I'm measuring as a X. So I'm taking a same material in the two different cases. I'm taking the two different points in that material A and B with a distance X. Now I'm applying the force on this body. So this type of force I'm applying, this we call as a pull force or tensile force. In both the cases I'm applying the same load, tensile load applying. In the first case, if the distance between the A and B is not changing, distance between points A and B is not changing, means even if you are applying the load, the distance between A and B after loading is a X. So that body we called as a rigid body. This means both the points A and B is same even after applying the tensile load. So that is still in X distance after applying the load. Coming to this case, I am applying the tensile load on these ends. So initially the distance between the point A and B is a X. So after applying the load, the distance between A and B is changes. So initially, before applying the load, the distance between points A and B is X. Now the distance between A and B is X plus 5. This means X is increases. So this means the body is a deformed. So that mechanics is called deformable body mechanics. So rigid body means when you are applying the load on any member, the distance between the 2 points is not changing, is called a rigid body, and that mechanics is called a rigid body mechanics. If the A and B, the points between A and B is changes, when you are applying the tensile force, the X will increases. If you are applying the compressive force, definitely the X will be decreases. So in this case, whether you apply the tensile force, whether you apply the compressive force, the distance between A and B is a changes. So that is called deformable, means the body is a deformed. That is under deformable body mechanics. Again, so the rigid body mechanics, again we classified into two different classifications. The first one, statics, and second one is a dynamics. In statics only, so the mechanics of residual body mechanics under statics, we studied pure engineering mechanics. Static condition means the body is under pure static, means even after varying the time, the body in the same position. So the time is even if the time is varying. For example, if I'm applying the 10 kgs load on the body, so after some time, that still is in the 10 kgs of load. That is called statics. So the example that we will discuss, we will study it in the engineering mechanics. In engineering mechanics, only external forces only considered. So coming to the rigid body mechanics of dynamics, we studied in a theory of machines, SOM, theory of machines. So coming to the mechanics of deformable body, can be classified into, again, statics and again dynamics. Again, from statics we can classify it into two different types. The deformable body can be classified into solids as well as fluids. So under two categories, solids and again fluids. The solid mechanics, again we can classify it into statics as well as dynamics. Is it clear? So what is the difference between the solids and the fluids? For example, so I'm taking a solid body here. Again, I'm taking another body. So here I'm taking a fluid on here. So this is a completely solid body. This is a fluid. Okay. So I'm applying some force on this solid as well as liquids, means fluids. So I'm applying the load on a solid as well as a fluid. This is a solid, this is a fluid. So I'm applying the load on the solid as well as a fluid. Now in solids, if you are applying the force and removing the force, the deformation is in the small amount. Means the deformation is only a certain point only. Is it clear? For example, this is a solid body. This is a solid body. So I'm applying the force. I'm applying the force. The body is deformed. The body is deformed. If you remove the load, the deformation is stops. Is it clear? So that is called solids. So coming to the fluids. So this is my phone. This is a solid. I am applying or pouring a liquid on this mobile. So if you are applying the force on this liquid or fluid, what happened? If you apply the small force on this, maybe if you apply the small force on this flow in this fluid, the deformation is continuous. The deformation is continuous, even the small force you apply. So the difference between solids and fluids is, when you applying the load on the solid, the deformation is in a particular point of time only. Okay. if you are applying the same force you applying the on fluids, the deformation is continuously, even you apply the small force. So after after you remove the load, the fluid is continuously deforming. That is called fluid. But after removing the load on the solids, the body does not continuously deform. That is called solids. Is it clear? But in a solid mechanics, solids, there is no change of, there is no deformation if you are apply the small force. But in fluids, if the force may be small, the deformation is continuously. That is called fluids. So coming to the solids, again we can classify it into statics as well as a dynamics. Again, the statics, what we studied in strength of materials, and dynamics parts we study in vibrations. Now we are in this topic, strength of materials. So the mechanics of deformable body under solids under statics is called strength of material. So I am repeating, the mechanics of deformable body under solids under statics we studied in a strength of materials. That body is called strength of materials. Is it clear? Now we will go for the next topic. Yeah. So in strength of materials, so the rigid body of the mechanics of rigid body under statics is called engineering mechanics. In engineering mechanics, only external forces is considered. But in a strength of materials, we consider internal forces also. This is very, very important strength of materials. In engineering mechanics, in first year engineering mechanics, we consider only external forces on any body. But in strength of materials, we should consider internal forces that we called as a internal resistance forces we consider. Is it clear? So in strength of materials, the internal forces we should consider. So we should calculate the internal forces that we called as internal resistance forces. Is it clear? So I'm taking a body like this. So I'm constraining at the one end. So this is I'm constraining. So when you're applying the load, some force I'm applying. So this is called external force. External force. To withstand this external force, definitely there should be an internal resistance forces generated. For example, this is my hand. If I am applying the tensile force on my finger, this is my finger. If I am applying the tensile force on this my finger, to withstand this external force, definitely in this joint there should be an internal force should be generated to withstand this external force. If it is not generated, what happens? If I am applying this load on this finger, then my finger is plucked out from the removed from this my broken out from this joint. So for withstanding for static condition, there should be definitely there is an internal resistance force is generated to static of this finger, to static equilibrium. So I am applying the external forces. So till now in engineering mechanics we consider only external forces, but in strength of materials we should consider or we should always think about the internal forces. So withstanding of this external force or for static equilibrium condition of this body, definitely there will be a internal resistance force is generated. So this is external force. To withstand this external force for a static equilibrium of this body, definitely there should be internal forces is generated. So this is called internal forces, Fi. So in strength of materials, the main aim of, therefore, the main aim of SOM is to develop equations for internal forces. So that internal force we should calculate. So due to that internal force, what are the different categories is generated? What are the different parameters are involved due to that internal force? We should consider calculate in strength of materials. So after finding out equations for developing equations for internal forces, we should calculate stress and strains in the member. So this internal force is called pain in the member. For example, so this is my finger. So I'm applying the external force on this member. This is external force. Due to this external force, definitely there should be internal forces generated. That internal force is cause of pain in this joint. So definitely I'm applying a huge amount of load. So what happened? There should be pain is developed. So due to that internal resistance force, the pain is developed. Therefore, the pain is called, we call as stress. Definitely there is a stress is applied on this joint of this finger. So definitely after stress is developed, there should be some change of dimension is there. It's maybe, or sometimes it may be, sometimes there is it may not be deformation in this body. So that is called as a strain. So the pain in the member, so the internal resistance force is cause of stress as well as, so this internal resistance force is cause of stress as well as a strain. So the main aim of strength of materials is to develop equations for internal resistance forces. The internal resistance forces is a cause of stress as well as a strain. So in entire strength of materials, we should develop equations for stress and strain. So after developing a stress and strain equations, we should design any member or solid member or any mechanical, any machine components with the help of mechanical properties. So after completing of this all these introduction, we should learn for mechanical properties of any material. Okay, so now yeah, so after developing equations for stress and strain in strength of materials, we should know some assumptions of strength of materials. So that is the first one is a homogeneous material and isotropic material. So this is very important assumption while studying strength of materials or designing of any component by using strength of material concept. So what is meant by homogeneous and what is meant by isotropic? So I'm taking two different bodies. So same bodies in two different cases. This is case one. So I'm taking three different points. So I'm taking so every material having some material properties like Young's modulus E, and bulk modulus K, and shear modulus G, and Poisson's ratio mu, and like this. So every material having some mechanical some material properties like Young's modulus or modulus of rigidity and bulk modulus and shear modulus or Poisson's ratio, like all these are the some material properties. So I'm taking the first case. This is case one. So this is point 1 and point 2 and point 3. So at point 1, this is the Young's modulus in the right direction. This is the Young's modulus in right direction. This is the Young's modulus in the towards the right direction. So this means in a given direction, so what we can observe here, in a given direction, at any point, like point 1 and point 2 and point 3 and in given direction. So here the given direction is the right side. So in a given direction at any point like 1, 2, 3, the material properties is same. The material properties are same. Am I right? So the material property at point 1 is E, and material property at point 2 also E, and material property at point 3 also E. That means in a given direction. So I'm taking the first at point 1, the material property of E is the towards right. At point 2, that material property is E and towards right. Even the third point also the material property is E, and even that is the direction is right. So in a given direction means in the right side direction at any point at point 1 and 2, the material properties is same, is called homogeneous material. Homogeneous material. So coming to the isotropic, at a given point, I'm taking at point 1, this is a particular point. At given point, any direction, the material property will be same in all directions. So I'm taking a given point. So this is a material property. This is a material property in y direction, x direction. This is a material property in a z direction. So at a given point, I'm taking a point in all directions, x direction, y direction, and z direction. The material property is same. So in x direction also the material property is also E, and the material property in y direction also E, and material property in z direction is also E. From at a given point, it starts from here point. That property is called isotropic material. So isotropic material. So not only E, for example, I'm taking K also. This is K, this is K, this is K. The material property in all directions, particular point, is called isotropic material. So here also not only E, any point, any material property is same. So my question is, so this is my question 1. So I'm taking again 2 different cases. Now this is point 1 material property E, this is point 1 material property E. Again same case, this is a point 1, this is point 2 at material property. So what is this case? So what homogeneous material says that at a given direction, so at point 1, this is a point 1, this is a point 2, right side direction material property is Z, and point 2 also the given direction material property is Z. So that we called as a homogeneous material. So here also at point 1 also material property E is in right side direction, and point 2 also the material property in the right side direction. So this is also homogeneous material. Am I right? Now, so I'm taking y direction. This is E. This is also E. So this is still in homogeneous material. And compared to the y direction, upward direction at point 1 also E and point 2 also E in the same direction, y direction. So still is in homogeneous. In z direction also this is E. In z direction also this is E. So even at a z direction, the material property is E, and at a point 2 also material property is the homogeneous. And what it says, at a given point, all the direction, the material property is same. So then it is called as a, again, isotropic material. So in this case, the material is a homogeneous as well as a isotropic. This means homogeneous may be isotropic material also. So homogeneous may be, the homogeneous material may be also isotropic. Now coming to this point. So this is my 2E. This is my 2E. So upper side towards y direction at point 1 is a 2E, at point 2 is a 2e. Still is it a homogeneous? And at point 1, z direction, this is a 3, and point 2 also z direction is 3. So still is an homogeneous, but this is not a isotropic because at point 1, so what isotropic tell that at a given point the material property is same in all direction, but at a given point at point 1 the material property in x direction is e, but y direction is 2e, but z direction is 3. This means this is a non-isotropic. And second point also, at second point at a given point in all directions the material properties is not same, different. X direction is e, y direction is 2e, and z direction is a 3. This is a non-isotropic material. Is it clear? So we can say that isotropic material may be homogeneous. Homogeneous material may be isotropic. Homogeneous material may be non-isotropic. So we can write the statement as homogeneous material may be isotropic or non-isotropic. So most of engineering materials, most of strength of materials, the material properties is we called as a homogeneous and isotropic assumption. So most of the design of any strength of material, any strength of any material, the material property is a homogeneous as well as a isotropic, but except of wood crystals. So wood crystals, except of wood crystals is not maybe homogeneous as well as isotropic. It may be homogeneous or non-isotropic, or non-isotropic or homogeneous, but wood crystals may not homogeneous as well as isotropic. So the most of engineering material properties is homogeneous as well as isotropic. So while designing, we should think of, and this assumption is very mandatory, should remember. So now our question 2 is, again I am taking the two different materials. So same two different cases. This is case 1, this is a case 2 again. So I'm taking point 1, again point 2. Is it clear? So what is this? E at point 1. This is also E. This is also E. At point 1, what is the material property? Yes, isotropic. So this is a 2E. 2E in y direction at point 2. 2E in z direction point 2. So even this is a isotropic. Now, same case. So this is I'm taking 2E and 2E and 2E. Again I am taking here 2E, 2E, 2E. So at given direction, given point, all direction material point is same, isotropic. But at any point, at point 1 and point 2, the material property is E here, 2E is here. So this is a different, this is a non-homogeneous. Coming to here, this is a isotropic plus homogeneous. So the isotropic material may be homogeneous. See, the isotropic material may be homogeneous but may not non-homogeneous. So this is a independent. So isotropic material is a independent, but homogeneous material is a dependent because homogeneous material may be isotropic, non-isotropic, but isotropic material also may be non-homogeneous and homogeneous. And my last question is, so this is my point. This is my body, any body I'm taking. So this is a E1, E2, E3. What is this body? So at given point, at all direction, the material property is different. This is a non-isotropic. Again, this is a E4, this is a E5, this is a E6. Again, this point also non-isotropic. But in a given direction, E1 and E4, this is a non-homogeneous material. So this is very, very difficult. So in strength of materials, it is the biggest problem. The biggest problem while designing of a non-homogeneous and non-isotropic material. So the designing of a non-isotropic and non-homogeneous is a biggest problem in the strength of materials. Now, our next topic is a load. So what is in by load? Yeah, it is an external force or moment on a member is called load. So an external force or moment on a member is called load. For example, I'm taking a body is constrained like this. Constraint means one end is fixed. So I'm taking another case. I'm taking a constrained body like this. In case 1, the force may be perpendicular, means this is a force P. This calls a transverse force. Transverse force. So the force may be axial force. This is axial force. So the external force on a member, this is a member. On this member, you can apply the force maybe in y direction, the force may be in x direction, the force may be in a z direction. So the y direction force is called as a perpendicular force or transverse force. Technically, we called as a transverse force. And the x direction force we called as a axial force. So axial force means, so this is the axis of this member. So the parallel to the axis, axial force means parallel to axis. Transfer force is a perpendicular to the axis. So this is a external force on the member. So this is called load, or we can call it as a moment on a member. So it is in a moment. For example, I'm applying. So I'm taking a 3-dimensional member. Is it clear? So I'm applying the force like this, in this way, on this way. So the what happened? The body is member may be rotating. This is a moment, or likewise. So this is experiences. This would be experiences like this. This member may be twisting like this. So if you are applying this type of force and this type of force, this may be movement. This will be experience like movement. Or if you apply, if you are taking a member, if you apply this type of force, this name, it is maybe bending. So this is called moment. So load is nothing but an external force or moment applied on a member is called load. So the load may be of any types. So types of loads. Types of loads. So the loads may be categorized into some important point aspects, that is based on direction of loading, and number two, based on extent of loading, number three, based on dimensions, number four, based on variation with respect to WRT means with respect to time, and based on load application time. So the loads may be categorized into some important types based on direction of loading, based on extent of loading, based on dimensions, based on variation with respect to time, based on load application time. So the first category we can classify it into two types: longitudinal loading and transverse loading. So longitudinal loading means, so I'm taking a member like this. So this is the axis of this member. This is the axis of this member. So along the axis of this member is called as a longitudinal axis. So this may be transverse axis. So if your applied load is along the direction of longitudinal axis, that is a longitudinal loading. If your applied load is along the parallel to the transverse axis, so like this, that we called as a transverse loading. Again, longitudinal loading and transverse loading are two types of eccentric. So the longitudinal loading is maybe pure axial or eccentric. For example, this is a member, this is a longitudinal axis, this is a transverse axis. If we apply load on the applied load is a same on longitudinal axis, this is pure axial loading. Otherwise, if your load, another member, this is a longitudinal axis, if the load is parallel to the longitudinal axis, so this is also load is parallel to the longitudinal axis, this is a load is parallel to the longitudinal axis, but the load is exactly on the longitudinal axis, that is a pure axial loading. But the load is somewhere the distance between the longitudinal axis, this is called eccentric loading. Is it clear? So this is a longitudinal loading and a transverse loading. So longitudinal, this is a longitudinal axis, this is a longitudinal axis, this is a transverse axis. If your applied load is parallel to the longitudinal axis, that is a longitudinal loading. If your applied load is parallel to the transverse axis, like a perpendicular, it's called a transverse loading. Again, longitudinal loading may be pure axial loading or eccentric axial loading. So pure axial load means the applied load is exactly matches on the longitudinal axis. Likewise, this is a case. This is a pure axial loading. If your loading is a eccentric means the load is parallel to the longitudinal axis but not on the axis. That is called eccentric loading. And based on extent of loading, point load, and B, distributed loading. point loading and distributed loading. Now I'm taking a chair. So I'm taking a chair. This is the 4 legs of this chair. So if a person is sitting on this area in this base, means entire that person load is distributed over this plank, this base plank. So the load is completely acted. This base plank is called distributed load. But that the entire chair force and that person force is acted on each individual legs. So this individual leg force is acted on this area, this plane, this point. This individual leg force are acted on this point. This individual leg force acted on this point. This individual leg force acted on this point. Different points. This all these 4 are point loads. Is it clear? So I'm taking, this is my mobile. This is my mobile. If the load is acted exactly on this point, this is a point load. Or if the load is acted entire this surface, this entire surface is called distributed load. And coming to the based on dimensions, the force is directly proportional to volume, or the force is directly proportional to area, or C, the force is directly proportional to length. So example, the force is directly proportional to volume is, some examples is there: buoyancy force, weight force, and centrifugal force. And force is directly proportional to area. I'm taking, this is an example. Force is directly proportional to area. So I'm taking pressure is equal to force by area. Then force is equal to pressure into area. Means the force is directly proportional to the area. When the area increases, the force also increases. So based on dimensions, the force may be directly proportional to volume like buoyancy force and centrifugal force. The force is directly proportional to area like pressure force. The force directly proportional to the length, that is a surface tension, because surface tension sigma is equal to force upon unit length. Is it clear? Then force we can write as a surface tension into length. So that force is directly proportional to length. The surface tension is directly proportional to length. So when the length is increases, the surface force is increases in a surface tension. And next one, based on variation with respect to time, that is a static loading. And second one, B, dynamic loading. So what is meant by static loading and what is meant by dynamic loading? So coming to the static loading, so I'm taking a member. I'm taking a member is constrained like this. Okay. So I'm applying a force on 50 kgs or 50 newtons. 50 Newton force is applying at 8 a.m. At 8 a.m. I'm applying a 50 Newton force applied on this member, this constrained member. So after 1 hour, I'm calculating, I'm measuring that load even after 9 a.m. That is also 15 Newton. At 10 a.m. also, the load is still in 15 Newton. So same constraint body. So I'm taking a constraint body, applying a 15 Newton at 8 a.m. So if you're calculating that load after 9 a.m. and after 10 a.m., after 10 a.m. or 11 a.m., after every frequent period of 1 hour, even that load is the same. That is called static loading. Means the load is not varying with respect to the time. Means load is not varying with respect to time is called static loading. Simply we called as a dead loads. Example, fan rods like this. So the fan is hanged to the fan rod. The weight of the fan hub and blade, all these are like maybe 10 kgs. Even 8 am also the fan weight is 10 kgs, or night 8 am 8 p.m. also 8 kgs. Another day in 8 am also same 10 kgs. Means every day with respect to time the load is not varying on the rod. The fan load is not varying on the rod. That is called with respect to time. There is no change of load. Force is called static loading, that we called as a dead load. Simply that we called as a dead load. And dynamic load is called with respect to the time, so opposite to the static load. So with respect to the time the load is varying. For example, if the load is applied on the member is 50 newtons on 8 am, after 1 hour if you are coming, if you are coming and measured at 9 am, if the measured force is varying other than 50 kilonewton, it may be decrease or increases, that is called dynamic. This means the load is varying with respect to the time is called dynamic loading. And the last one, it is very important aspect in a strength of materials point of view. So that is based on, so this is very important, based on load application. This is very important as per a strength of materials point of view. So that may be number 1, gradually applied load. Okay. Number B, okay, based on load application, this is very important, gradually applied load. B, suddenly applied load. And C, shock load. And D, impact load. So what is a gradual applied load? What is a sudden load? What is a shock load? Let us see. So I'm taking a member like this. So initially this is constraint. So I'm taking a tie bar to this one. Okay. At 9 am, I am applying 1 kg load. And at 9:15 am, again applying 1 kg load. Again at 9:30 am, I am applying another 1 kg load. Again after 9:40 am, I am applying 1 kg load. Means every 15 minutes, the time varying is a constant. So the load is applied gradually. So 1 kg, 1 kg, 1 kg, 1 plus 1, 1 plus 1, 1 plus 1. I'm applying the load gradually. I'm applying the load. So gradually I'm applying the load at a frequent interval of time. That is called gradually applied load. So example for this is a tensile testing load. So while conducting the tensile test of any specimen for finding out the tensile strength and ultimate strength of this material or strength of material, we should conduct some tensile test and UTM mission. On UTM mission, we should apply the gradually apply load. So gradually you should apply one by one, slowly you are applying the load. So sudden load. Sudden load means the load applied or comes suddenly. Load comes suddenly when h is equal to 0, height is equal to 0. So the example of sudden load is, this is a brake shoe, so brake drum. This is a brake drum. This is a brake shoe on this drum. So when you are applying, so if you are going a smooth in a road smoothly, suddenly if the obstacle is coming or suddenly obstacle is avoiding, what should what should you do? Suddenly you applied the brakes. You suddenly applied the brakes. This means the load is acted suddenly, means the height between the shoe brake and the brake drum is almost 0. There is a negligible height. Though the load is comes suddenly, the shoe brakes suddenly contact to the this brake drum with the height 0. Even there is a height, that is a negligible height. That is called suddenly applied load. So without intimation. So that is applied the load. Sudden load comes suddenly with a huge less amount of height. That is called sudden load. So the shock load. Shock load is nothing but without intimation. Load comes without intimation. Example, bomb blasting. So the bomb blast always that is no intimation, it comes suddenly. That is called shock load. Shock load is nothing but load comes without intimation suddenly. That is called shock load. So example is a bomb blasting. So in shock load, the intensity of load is very high. Is it clear? And coming to the impact load, this is a planned version of shock load. So this is a impact loading. So shock load is a without intimation, huge amount of load is suddenly acted on the member. But impact load, this is also the intensity of the loading is very high, but there is a planned version. So you should plan to apply the sudden loading. For example, punching press and punching dice and blow hammering on the any material is called impact loading. So this is some introduction of strength of material. So in our next class, we will go and discuss about the stresses. What is best stress? What is best strain? What are the different types of stresses? And what is different types of strains?